So now we have to analyze the modular behavior of the Eisenstein series G2. But first of all, I would like to formulate a nice fact as an exercise. You can find the proof of this fact in the paper, in the famous paper of Richard Borchers from 1995 about automorphic product, but you can prove this fact using the description of the kernel of modular operator. So I can rewrite this fact that delta belongs to the kernel of D12. So maybe I can put the first question, this is an elementary question, to analyze the kernel of this modular differential operator for any k. Any k. And then the fact, very nice lemma from the Borchers paper. Then the following map from the space of modular function with respect to S to Z into the space of weak modular form of weight 2 with respect to S to Z, then this map is surjective. I repeat, then you can prove this fact using the definition of modular differential operator. Moreover, the corollary from the surjectivity of this operator, if f in tau is a weak modular form of weight 2, then the constant term is always 0. Certainly, this is direct corollary of the fact 2. Now, we have to analyze modular equation of the Eisenstein series G2. This is the modular equation of the logarithmic derivative. This is, I can rewrite definition once more. This is 1 minus 1 over 2 pi I n prime in tau over eta in tau. So, modular equation. First of all, let me write down the modular equation of the Dedekind eta function. Multiply a system in M, so a root of order 24, C tau plus D to the power 1/2 eta tau for any M equal to A, B, C, D in SL to Z. What do we have for n prime? So let's calculate the derivation of the left and the right hand side. So what we get? c tau plus d to the power minus 2 n prime a tau plus b over c tau plus d is equal, now without any changes, v eta m, the homomorphic factor, n prime tau plus v eta in m c over 2 c tau plus d to the power 1/2 eta tau. And now we have to divide the first term by the second term, and we have to add the constant term minus 1 over 2 pi I. What we get? We get c tau plus d to the power minus 2 g2 in tau is equal, oh, I'm sorry, here I made a mistake, g2 in a tau plus b over c tau plus d is equal, the first, we have to divide the first term by the right hand side, so we get g2 in tau. Then we have to consider the second term, and we get, with this additional coefficient, get minus c over 4 pi I. Maybe I change a little the form of this factor, 1 over 4 p pi I c over c tau plus d. And this is true for any m in the modular group. We see that the Eisenstein series G2 is not modular. So G2 is a quasi-modular form of weight 2. This is simply by definition, because without this linear or fractional linear term in c tau plus d, we would have a modular form of weight 2. But this additional term certainly changes the behavior of our function. So this is the difference between modular and quasi-modular form. But now we have to put the question. So we have to calculate the differential operator, modular differential operator, in Eisenstein series E6, E8, and so on. But what is about G2? So the question which we have to put, what do we have about D in G2? If we calculate the derivation of this modular equation, we get a term of order 2. So you can check that if we add here the coefficient 2 G2 multiplied by G2, G2 to the square, we get a function which transforms like modular form of weight 4. Please check this. So it means that this sum has very good modular behavior with respect to the full modular group. But now you can calculate this function, because to calculate it, we have to analyze the constant term. The constant term we have only here. Yes? And calculating this constant term, you can find that this function is equal up to some constant to the Eisenstein series E4. I leave to find this question to you. Certainly the coefficient here, this is 2 times 1 over 24 to the square, so we have something here like 1 over 2 times 12 to the square. Please find this constant. But now we can make the conclusion from our calculation. In fact, we have proved a nice theorem about the space of quasi-modular form, but I have to define this space, and I can make this definition inside the theorem, but I would like, sometimes we use two notation for our quasi-modular form. Means we use from time to time the following notation: E2, this is 1 minus 24, the sum sigma 1 n q to the power n greater or equal to 1. This is our Eisenstein series G2 with coefficient minus 24. G2 into. Please compare the Fourier expansion. So I would like to analyze once more the Eisenstein series. So the Eisenstein series E has the first Fourier coefficient 1. So E series, E Eisenstein series, all of them start by 1. And I would like to define the same Eisenstein series for weight 2 up to the constant minus 24. This is the quasi-modular Eisenstein G2. And now I can formulate the theorem and to define the space of quasi-modular form. Theorem. The graded ring of all modular form with respect to SL to Z is generated by two Eisenstein series E4 and E6. Its extension by E2 means the graded ring generated by three Eisenstein series. The quasi-modular Eisenstein series E2, E4, and E6. This ring is called the ring of quasi-modular form. And we prove that differential operator D acts on this space. Means the ring of quasi-modular form is invariant with respect to action to the differential operator D. This is the first fact. The second, without proof, but you can do it by yourself, this is not complicated. E2, E4, and E6 are algebraically independent. This exercise. Now we can consider the method of automorphic correction.